Yeah, so sorry for the interruption. So what is MAE? It's actually a very simple idea. Given an image, you mask a proportion of it, and for the remaining ones or remaining patches, you feed it into an encoder and get the latent representations. And then you pad these latent representations with position encodings of the masked patches. And now it becomes a full sequence length again. And this full sequence length is fed into a decoder, and this decoder is used to reconstruct the original image by predicting the missing patches. And this entire input and output is operating directly on pixels. So I want to highlight that two things about this design, the high mask ratio and this encoder-decoder decomposition. So for MAE, we will use a larger encoder on the visible patches, and then we will use a small decoder on all the patches. And this is working very efficiently when coupled with the high mask ratio we apply to images. So typically, we will apply 75% of the mask ratio, so only keep 25% for the large encoder to operate on. So this is very efficient. And we just use a single projection layer to match the dimensions from the encoder to decoder, so to connect them. And here are some reconstructions from MAE. So in this case, we mask out 80% of the image. So maybe even for humans, it would take them 1 or 2 seconds to figure out what object it is. And in the middle, it's MAE's guess. It successfully guesses this is a butterfly. The image is a bit blurry compared to the ground truth on the right, but you can already, it's already reconstructing the shape gist well. And we have examples to show that MAE can generalize. It's not just memorizing the original image. So given an original image like this, we apply different mask ratios, and we actually get different output or different reconstruction results. So it's not just memorizing the original image. And for representation evaluation, as I mentioned, self-supervised learning is just a pre-training step. The actual thing we care about is during evaluation for downstream tasks. For MAE, we just take the encoder for evaluation. So we throw away the decoder. And the encoder is fed with full sequence. So all the image is fed into the encoder used for benchmarking representations. And here are some results. So this is a result for ImageNet classification. On the horizontal axis is the number of parameters, and the vertical axis is the fine-tuning accuracy. And we find the original transformer we used is overfitting heavily when we just train on ImageNet. And we can apply a lot of regularizations and augmentations, so we get a good recipe, but the improvement saturates when we scale up to models of 600 million parameters. And with MAE, we find that the model can actually have a healthy, scalable trend from VIT base to VIT huge. And at VIT huge, it's having a 4% gain over the baseline. And the trend is very similar compared to a model that's pre-trained on a large data set, GFT 300 million. So with that, we also tested on object detection for for another task to transfer. And there are two takeaways here. The first takeaway is that for object detection, the idea of doing masked autoencoding works really well. It improves previous pre-training method by 3 to 4%. And I want to highlight this number from training from scratch here. So you can see that this training from scratch or training from random is actually getting better results than supervised pre-training, the first row, and contrastive pre-training, Moco V3, the third row. And this means that if we find a good recipe for training from scratch, other types of pre-training actually doesn't help that much. So this is the MAE. And just to recap what I have discussed, I discussed reconstructive self-supervised learning. In the simplest form is autoencoding. We can do augmented form with some kind of transformations. And I highlighted a special transformation, which is doing masking. And the question I want to ask is, what about contrastive learning? So is contrastive learning kind of reconstructive or non-reconstructive learning? So for people who are not familiar with this, contrastive learning is something like this on the right side. So you have an image and you have two transformations of the image, and these two transformations will be fed onto the encoders. It's a Siamese encoder because the weights are copied. Oh, what's going on? Wait. Yes. Oh, no, this one. Where's the slides?
Which one is your slides? Did you accidentally?
I don't know. Yes.
Oh, I see.
Okay. Yeah, sorry. So for contrastive learning, it will get representations from a batch of images, and then it will compute the similarity and the dissimilarity among the images. So the specific idea is that it will try to enforce the similarity for the representations from the same image, and enforce dissimilarity for the representations get from different images. So I'm going to talk about something controversial here, that I think this is an implicit form of reconstructive learning. So this is still reconstructive learning. And the reasoning is something like this. So I'll talk about instance discrimination first, and then try to draw the connection for contrastive learning to instance discrimination. So this instance discrimination idea is very simple. So now you're not just looking at one image, you're looking at images from an entire data set. And because for self-supervised learning, there's no label, the simple idea is to not just predict the class labels, but try to predict the data IDs. So each data is becoming its own class. So one instance per class. And if we have 10,000 images in this data set, we'll have 10,000 classes. And in this way, the new data can be viewed as X dot dot. It includes the original image X, but it will also have an instance indicator I to indicate which instance it is. And the task is trying to predict the index the instance index as part of X dot dot. So in this sense, this is still reconstructive learning for instance discrimination. And for contrastive learning, it's very simple. Because instance discrimination is trying to predict the index from a fixed set. So if you have 10,000 images from in the data set, you have 10,000 indexes. But for contrastive learning, because it uses a CMS network, it actually provides a dynamic set. So it will randomly sample, for example, 4,000 from the 10,000 data points, and use that as a set, as a candidate set for the model to predict the index. So in this way, contrastive learning can also be thought of just trying to recover the index from the data. And we can easily augment contrastive learning with some kind of transformations. And now it will become X dot 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 because you have an X transformation and the instance indicator. And the task is still trying to predict the indicator as part of X dot dot dot. And indeed, this is what people do. And you will hear people talk about all kinds of augmentations or transformation engineering for contrastive learning in the previous years. And I would say that without these transformations, contrastive learning is actually a rather weak reconstructive learning. And the augmentations are just trying to make the task harder to make the representation meaningful. Otherwise, if it is just on the original data, the model can cheat really quickly, really easily, and does not learn meaningful representations. So I talked a lot about reconstructive learning. Next, I want to talk about something that's non-reconstructive, something that not try to predict X or part of X, but something else. But does non-reconstructive learning even work? Because if it is trying to predict something else using the input X, wouldn't it simply just ignore the data itself? Because anyhow, the model wants to predict something else. And indeed, the model is very easy. It's very prone to ignore the data. And this is some important issue, a crucial topic for research in non-reconstructive self-supervised learning. And I'm going to use our example, SimCM, as a non-reconstructive self-supervised learning framework. It works, but underlying mechanism is still not clear. So that's what I'm going to briefly talk about. So for SimCM, the idea is very simple. We still have these CMS networks. We have an input X, and we transform it into X1 and X2, feed them into the same encoder twice. And we have a predictor on the left side, and we have stop gradient on the right side. And here, the loss or the thing that the network wants to predict is simply the similarity between images, between augmentations from the same image. And I would argue that because contrastive learning, it tries to predict both the similarity and dissimilarity, it does an explicit reconstruction of the index. But because in SimCM, we only predict the similarity, and the target can just be one in some sense, because it's cosine similarity. So no reconstruction of the input is done here. It's predicting something else. And here is the SimSam algorithm. I won't go into the details, but I would highlight that we use the symmetrized loss. So the predictor is applied once on the left side, once on the right side, and the loss is computed twice. And we use a simple cosine similarity. So the target is always 1. We want to maximize the cosine similarity there. And then there's a gradient, and the gradient is only backpropagated through the predictor, and there's a stop gradient on the other side. And here is the most crucial analysis for SimSam. What we find is that stop gradient is crucial. Without it, the representation indeed collapses, and indeed it ignores the data that feeds into the network. And we have several indicators. For example, the loss curve, it quickly finds the global minimum, or the k-nearest neighbors on the right side to indicate that. And we also did some analysis on the predictor to show that this is important, but it's not as important as the stop gradient. And we have experiments in the paper to show that predictor can actually be removed, and the representation still won't collapse. It learns from the data. And I want to put SimSam in the context to compare with other Siamese learning frameworks. So here I'm listing 4 of them. In fact, you have already seen the top left one and the bottom right one. The top left one is a simple contrastive method, and the bottom right one is the SimSam. And in the middle, there are 2 other non-reconstructive methods for self-supervised learning. So one is called bio. It uses a momentum encoder, so which is to do exponential moving average on the encoder weights compared to SimSam. It also has a predictor, and because of the momentum encoder, the gradient is also not backpropagated on the right side. And the bottom left one is the swap. So this is an online clustering algorithm called Sinkhorn-Knopp. It tries to balance the cluster assignments, and the goal is to predict the cluster assignments there. And the cluster assignments is also created on the fly. So I would regard this also as a non-reconstructive self-supervised learning method. And compared to these methods, SimSam can be regarded as SimClear without negatives, swap without online clustering, bio without momentum encoder, and compared to MoCo, which I didn't show, it removes both the negatives or contrastive learning and the momentum encoder. So no momentum, no contrast also works, is a takeaway from SimSam. So I've talked about these 2 paradigms for self-supervised learning. One is reconstructive, the other is non-reconstructive. For the remaining time, I'm going to talk about a less known observation we have made when we study Siamese learning. So this is to study the asymmetry for Siamese representation learning. So here I'm listing more frameworks. I think some of the frameworks are also mentioned in previous talks. But the common similarity between all these frameworks is that it relies on the Siamese architecture. So we'll see some kind of symmetry between the left side and right side, or the top side and bottom side. And one is used as a target, the other is used as a source to compute the loss. And it's not quite yet that Siamese learning just works out of the box. We actually find that there are a lot of asymmetries in Siamese learning. So for example, for MoCo and bio, there are momentum encoders on one side, but not on the other. And for bio and SimCM, we find predictor is important. And for SimCM and a Dino, some kind of a stop gradient is applied over there on one side, but not on the other side. So this motivates us to think about how important asymmetry is playing in seamless learning. Of course, sometimes the asymmetry is super important. It's crucial. Otherwise, the framework won't even learn from data. It will just ignore the data and collapse. But here, what we are interested in is something else. So if the framework already works, is adjusting asymmetry can help or hurt. So to do that, we do this abstract form of seamless learning. So we have a source one on the left side, and we have a target one on the right side. And again, we use X and with two transformations to feed both networks. And then the loss is computed by comparing source and the target. And in the literature, there are a lot of other ways to call these two branches. So one is for the source, one can call it query or the online encoder or the student encoder. For the target, sometimes it's mentioned as a key encoder or teacher encoder. And this abstraction actually also covers symmetric frameworks. So for example, SimClear, if we do online deduplication, so you just online duplication. So just copy the weights online when we do the learning, but the gradient is only backpropagated on the source side. So the main takeaway from our study is that this variance, I'll define the variance later. The variance should be higher, relatively higher on the source side, and the variance should be relatively lower on the target side. And there's a high correlation between this relative source target variance and the learned representation quality. And we find this observation generalizes really well. So we had a lot of designs, tried a lot of different self-supervised frameworks, and it generalizes to all the settings we have studied. So to define the variance, I would like to first say something about the encoding. So the encoding is the encoder's output given an augmented view of images. So with this, there are three sources of variance. The first is changes to the encoder weights. Of course, it will cause a change in the encoder output. If we change the image, of course, it will also change the output. And if we change the view or the augmentation, it will also change the output. So what kind of variance is of interest here? For the changes of encoder weights, it actually has already been successfully demonstrated in momentum encoders, because momentum encoders is an exponential moving average of the online encoder. So it has a small variance by definition. So in that case, the momentum encoder is already a good justification that higher variance should be on the source and lower variance should be on the target. And for changes to the image, we find an interesting phenomenon that it only depends on the encoding dimensions. So here's a figure. So once we have started to training, this is using a MoCo V2, a contrastive framework, the variance with regard to the images will quickly converge to 1 over the number of dimensions of the encoding. One can actually prove that because we are doing L2 normalizations and do contrastive similarity learning on the top. But what this means is that the representation is dispersed or distributed really well in the space. So each image is mapped to a specific location, and it expands very well on the ball. So with these two contexts, our study of interest is to study the intra-variance, which is variance introduced from the view. So we did a bunch of studies with different augmentations, with batch normalization or synchronized batch normalization. We also did an explicit average, try to reduce the variance on one side. So I'm just going to show you with some examples. So the baseline we used is a MoCo V2. It's a contrastive method with some constants. And for simplicity, we didn't use any loss symmetrization. And our baseline already outperforms MoCo V2 by itself by adding a batch normalization layer. And the first study we had to study this asymmetry is multi-crop augmentation. So given this MoCo V2 contrastive framework, where should we put the multi-crop augmentation? And for context, we have shown here that multi-crop actually increases the variance by a lot, which is very intuitive. You do a very strong augmentation of the image, of course, it increases the variance. And we find that, we try to plug in MoCo V2. So we can either plug into the source side alone, target side alone, or both. And in this case, we find that the source target the source one benefits a lot from multi-crop augmentation. And it actually hurts the target if we put it on the target side. And we did the same thing with a new kind of augmentation in that work. It's called the scale mix. It again increases the variance. And we did the same thing and find it helps on the source, but not on the target. And we generalize it to weaker or stronger augmentations, not just with those special ones. And we find that weaker augmentation actually helps when we plug into the target. And for stronger augmentation, we find it helps when plugged into source. And we can do the combination of both. It also works. And beyond the augmentations, we tried to do something more technical. So one is try to compare batch normalization with synchronized batch normalization. And by definition, synchronized batch normalization will have a smaller variance. And we find that synchronized batch normalization helps when plugged in on the target side. And we can do it explicitly. So mathematics tells us if we average multiple encodings, it will definitely reduce the variance. So that's what we did. And what we find is that if we reduce the variance, it is more helpful to put it on the target side. So to sum up, we have all kinds of different ways to manipulate the variance. And we find that whenever the mechanism is increasing the variance, it should be plugged on the source side. If it is decreasing the variance, it should be plugged on the target side to be helpful. And we did a lot of generalizations, for example, longer training. We tried other frameworks, so MoCo V3, SimClear, Bio, SimCM, and at that time there was also Barlow twins. We also generalized to other backbones, vision transformers, that's a backbone used by MAE as well. And all of them, we find the observation holds. And we can do compositions as well, but of course it doesn't always work. So we find with some kind of compositions, it can beef up the representation learning of Moco V2 to a really high number back then. And in general, composition helps, but it does not always help. So this is just the observation, and this observation is not 100% correct. And finally, we did some linear transfer for downstream tasks in order to compare with the state of the art. Actually, this is some older results, and it's less important. So the important takeaway is we find for such kind of CMS learning, the variance of source should be relatively higher than the variance of the target in order for anything to help. So if you have come up with some idea, maybe you can first try to measure the variance that this idea brings about. And now you will know which side this idea should be plugged into. So to summarize, I have talked about two paradigms for self-supervised learning, and I have talked about one observation we have made when we study self-supervised learning, especially CMS learning. So that's it. Thanks. You have a question here?
Yeah, I'm just curious if you think, oh my God, this is a lot. Okay. Do you think the observations generalize to medical images? For example, like an X-ray or some sort of MRI of the brain. And the reason I ask that is the sort of variation we see in those images is much less than natural world, just the natural world. And any sort of what do you call it? Any sort of variance in these would make them both
yeah.
We're going to look away and we find that. That makes sense.
Yeah, I think it makes sense. I do want to point out that it's not the absolute variance that matters in our observation. It's a relative variance that matters. So the source variance should be relatively higher than the target variance. So I would believe that it can still work, and it's less about the data, but more about this mechanism that we have a source and we have a target, and the target should intuitively be relatively stable. So stable is a way to describe low variance, and this source should be it's like a student, and it needs to be relatively explorative, so it should have a higher variance. So that's my understanding of it.
Thank you. I first want to first the question maybe more about the technology slides, and we said very low variance for natural images. The cells with powers is very similar, but we define the side actually fall when we try something like stronger conditions in the teacher and you found it like trial and everything. So sometimes what's better is now and letting me back so we're going to why instead of even programs.
Thanks.
One question that you did, so this was like on the images, do you have any intuition or insight about some installation part of these algorithms where they also the variance this similarity or the fact that these algorithms were is due to some other let's say thank you.
I'm not sure I get the question, but
So that does the self-exploration or like the
momentum.
Does that also related to this different, enforcement different variants on student or is it some other mechanism that is not related to
Yeah, so I think the momentum encoder, maybe I talked too fast. The momentum encoder is definitely related to this source, this variance observation, because momentum encoder intuitively is a smooth encoder. It has a lower variance. So the encoding it generates from the momentum encoder has a lower variance. So it is always put on the target side. I mean, it has to be on the target side now, but it also coincides. I mean, it's not like a coincidence. It is the momentum encoder is helping in that way.
Thank you. So, it's very similar to the first question when medical images, especially MRI images, are taken. The self-supervised learning is predominantly done in the measurement domain rather than the image domain. For instance, in MRI, the acquisition is in the Fourier domain. So, the self-supervised learning is more done in the measurement space than in image dimension. So the measurements are also less. As a result, the acquired data itself is degraded. And using only those measurements without relying on the ground truth, the learning is done to reconstruct the high quality image. So when using such measurements, especially complex numbers and Fourier space measurements, are there any challenges if you have suggestions in this?
I guess I'll take this question offline because I'm less familiar with the Fourier transformations and medical image, but I'm happy to discuss about it. Yeah, I haven't worked on medical image myself.
Yeah, I have two questions for you. One is that I think in 2020 there's a paper talking about like one SSL is effective and have some there's some paper basically they say that SSL is less effective if you have more than 500,000 of images. That's actually in
I do want to say that it's not as effective as text right now. So compared to large language models that can use a ton of data and do self-supervised learning on that, I think for images, we haven't seen a very strong improvement when we increase the number of images for pre-training. So partially that should be true, but I don't think I mean, with the latest techniques, I think we are already over the 500,000 number of images line.
And we
So-
should that follow-up question, still the fact that, if they doesn't like 9.5D or, common tool, like 12.8D, I mean, this kind of machine language training approach and creating this, transforming models where the self-supervised model, self-supervised is compared to, this, inherited approach.
Mm-hmm. Yeah, so I think this is something we think about a lot. I think a lot of the tasks that we are interested in computer vision right now has some relation to language. So this vision and language pre-training task is taking advantage of that in some sense. And and there are some tasks in computer vision that right now are not so popular, but they are catching interest. It relies less on language. So for example, control, low-level control. I think we are also doing explorations ourselves, but those are the tasks that are less related to language, but are still very important, and it should be looked at when we evaluate self-supervised learning methods. And the results I have shown here, they are all about semantic categorization or object detection, which is a lot of them is actually semantic categorization. So for those, I think language has language with a lot of data, it definitely has an edge over there.
Thank you for doing this explanations. So, in your point of view, mask auto-encoder and contrastive learning are very similar in that most can be viewed as a reconstructive self-supervised learning. And I agree to this point. And, there are some words that combine those frameworks, such as CON and C and E. So, if your two frameworks are similar, why do you think there is an increase in performance when they are combined?
Yeah, so I think my immediate answer to that is they are trying to reconstruct the different parts of the data, right? So X dot dot dot, it includes three things: the data itself, the image data itself, the instance indicator, and the transformation. And for contrastive learning, it's trying to reconstruct the indicator, and for MAE like method, they're trying to reconstruct the data itself. So reconstructing more maybe maybe is helpful over there. I guess it's lunchtime, so. Oh.
All right, let's give Xinlei another round of applause. Special thanks for his talk. Okay, I think that concludes our morning session. We'll be back around 1:30 p.m. For the afternoon talks. The afternoon talk going to be really focused on data efficiency for training as well as inference. Basically, how we can better collect the amount of data we need to train the large models, how we can make them efficient, how we can utilize the data effectively, and what will be the implications for all those different fronts. So look forward to meeting you guys again in the afternoon session. Thank you.